So we will continue with our speakers. And now I would like to invite Dr. Kurt Rohloff. He is the CTO and co-founder of Duality Technology. Don't know how many of you already heard about this company, but something very interesting. Of course, combining AI technology, but you will see in more details, doing algorithms and analytics on encrypted data in the cloud. So imagine yourself that you can really cooperate about sharing data without doing the decryption. So by definition, the data is encrypted not only in rest, not only in transient, but also during processing. So I will now allow and give the talk to Dr. Kurt.
Thank you very much for that kind introduction. So, as was just said, my name is Kurt Rohloff. I am the CTO of Duality Technologies. We're a relatively new startup and split between here in Tel Aviv and New York City. But we've been working on this kind of tech for several years. And so I've been sitting in the back up there and listening to a lot of these talks so far, a lot of very excellent talks so far today. And we've been hearing a lot about AI, about how to actually inherently protect the AI from data type attacks, pixel attacks, these kinds of things. We've been talking about we've been hearing about how AI can be used for actual cybersecurity, identify bad actors and things like that. And what we're going to talk about today, what we're talking about in Duality and what we're commercializing in Duality is a different stack of technologies, which is how one actually protects the AI itself, how one actually protects the data itself. And there's a couple angles from this. One of them being is that when you actually go and want to train an AI system, neural net, SVM, something like that, typically for those of you that were in academia, I did a stint in academia, what was the hardest part of doing ML research? Getting data sets, right? It was like the absolutely hardest thing, all kinds of weird agreements that you had to sign your life away and your first 3 children and things like that, get access to data. And, data is key. And, generally the providers of data don't want to release it. They're very hesitant to do so. But this has really hindered, in our view, a lot of the applications of AI outside of big siloed domains like a Google, Facebook, and things like that. The other side of that is that after you've gone through all this legal effort and expense and developed your own innovation in terms of ML algorithms and AI and things like that, you've built your model. And you want to start using it. Well, what's the services model for this kind of AI system? Do you actually just go and say, hey, here it is? For a lot of this is fine for a lot of us. But suppose you're a company like a Tesla or something like that, where you actually have to go and deploy these AI systems out in the real world, where there's always this threat that someone's going to go and reverse engineer it, or you put something on an app. And I've been around the industry long enough to know how easy it is to reverse engineer compiled code. And so this is always a major challenge too with these AI systems. Once you deploy them, how can you actually get them out and used and deployed in a way that their actual approach can't actually be stolen by someone else? And so we've been focusing on that at Duality, using a set of technologies that's basically called homomorphic encryption. But there's a broader set of technologies about encrypted computing, which is basically when you have data, how do you actually compute on the data while it's encrypted? And so I'm going to be talking about the high-level security model for this and giving a brief introduction for us. And I think there's a bunch of us in the room also. Our CEO, Alon Kaufman, I think he said he was here. Maybe he went out for a tea or something. Alon? Yeah, hi. And so there's a bunch of us here. You want to talk to us later. And part of this is this fear and this vision. And one of the things that we found as we've been going through our initial customers and things like that is that there is always this need for not just doing AI on data, but also doing AI on shared data, on collaborative operations, You might have multiple people with different data sets. It might be different data coming from different providers, for example, horizontal or vertically, that one will want to join and then learn on it. And as I said before, that once you actually learn it, go and actually use the data in some way. And so we had this fear in the vision, and so me being, based in New York City, of course I had to use a cartoon from the New Yorker. And the caption down the bottom, for those of you that are squinting in the back, is basically your previous provider refused to share electronic medical records. Not to worry, I was able to obtain all your information online. And this is kind of like the fear and the vision that we see, is that we want to enable these kinds of ability to actually go and pull data as a service and run on computation AI as a service and analytics as a service without having to be so very afraid of having your private information leaked. And also if you're a company or other organization that you don't take on don't take on unnecessary liability for sharing data without these very large onerous security agreements. And so, as I said, this advanced AI and data comes in many flavors. We have this one model here, which is basically the two sides of this, fairly simplistic. You have a data. You might actually want to go and protect the data, or you have this function. And so you want to enable some sort of third-party analysis on sensitive data or third-party execution of some sort of sensitive model. And then there's this data collaboration model of how do you actually go and different parties might have different data sets. Say, for example, different pharma companies or different insurance providers have different data sets, and they want to run some joint analysis about the effectiveness of some sort of drug or other treatment and things like that, without actually sharing the data. And then there's this other data set model, for example, you might have some sort of central repository, maybe government, maybe some other large provider, would want to join data, for example, from multiple medical providers and run some sort of analysis on it locally without taking on unnecessary risk about how data is joined and shared and accessed locally. So many different flavors for this. And so what we're seeing and what we're hearing from the market is that AI is a very, very scary business proposition for a lot of these reasons. Because AI is really all about accessing and evaluating data, and often very extremely sensitive data. Often data that's very complicated, and a lot of the traditional, more statistical-based techniques for doing de-anonymization, things like this, when you really, it's like this old line from this old Quentin Tarantino movie, that if you really absolutely positively got to be sure that the data is going to be protected, except no substitutes. And the trick with this is that a lot of these more statistical-based approaches have very well-known attacks where one can de-anonymize the data through relatively simplistic means. And as I said before, it's all about gathering, learning, enriching the right data, which requires sharing and collaboration on data, which is potentially extremely sensitive, both for business and privacy means. And the other side of that is the actual deployment, where not all owners have AI capabilities, algorithms themselves being extremely sensitive, model parameters being themselves extremely sensitive, and a lot of this is very critical IP with respect to the keys of the kingdom of business. We've seen all kinds of startups who basically develop these different AI-type models and built on special data sets that they go and develop, and then they need to protect to actually monetize those models that they build themselves also. And so this is being driven by a couple different needs. Although I've been talking more about the business use case, it really is about the ecosystem of modern information technologies. Partially, I'm sure I could rattle off all kinds of acronyms, GDPR and HIPAA and all these other kinds of privacy and regulation drivers for maintaining data security, maintaining those operations, but really being enabled by AI analytics with the need for security. And of course, although I didn't bring it up, this notion of deployment in the cloud, if you actually want to build these models. And there was I saw a really good talk yesterday that was talking about how when you actually build a model itself, and suppose you actually have a model, for example, like for facial recognition, and you build this model for facial recognition, and then one of your training participants actually comes and get his facial recognition identified for some sort of medical condition like diabetes or something like that, if there's, for example, a pegged 100% likelihood that someone actually has one of these conditions, usually that's a really good indicator that this person was actually in the training data set, which is in and of itself kind of its own little security hole that seems to be disregarded. But it's there also. And so how have we been doing that? And so we've been developing a set of text built around a number of different technologies around encrypted computing. And there are a lot of different flavors of these, and we have techniques in several of them. But one in particular that we've been focusing on is a set of techniques called homomorphic encryption. And so we're probably familiar with a couple different types of crypto, one being symmetric encryption, hide information so it can only be used by you later. This is the canonical AES encryption, symmetric key encryption, for example, protecting your legal files. I'm sure we've also heard about this public key encryption, which is hide information for an intended recipient, which is basically you have someone else, you take their public key, encrypt the information, and then it can only be decrypted by the intended recipient. For example, sending encrypted emails and things like that. Outside of that, and homomorphic encryption is this other flavor of this, is hiding information so you can actually outsource the processing. And one of the limitations of the symmetric and public key, at least the formal definitions of them, is that the ones that had existed up until several years ago did not allow processing. And so what we can do is that with homomorphic encryption, and the model is that take data, encrypt it, public key encryption, send it to someone else you don't necessarily trust, like the Amazon cloud, and then do analytics, processing, AI, secure collaboration on the data also. And that's homomorphic encryption, and there are variants of these kinds of encrypting computing technologies, secure multi-party and things like that also. We in particular have been focusing on one thing that's actually particularly nice about the major homomorphic encryption technologies is that they happen to be a family of encryption technologies that are post-quantum. Basically what that means is that they're resistant even to quantum computing attacks, which are starting to become increasingly a concern of large players like the nation states. And also has these nice properties associated with them where they're actually compliant with the current leading candidates for the NIST, NIST public key candidates for the next Suite B recognition. So kind of a nice aspect of these. But the fully homomorphic encryption models that we have, basically you start off with a client, your phone, something like that. You want to get access to your, some sort of analysis on data. And that data might come from some sort of source, whether it's from your email or from your medical doctor or something like that. And you have a computation host, some server, some sort of cloud server. You encrypt the data on this, at the source, send it to the computation host, take some computation, and that computation could be, for example, analytics, like a neural net model or something like that. And although it's not actually, I'm sorry, it's not here in the slide, this actual computation itself, the model you want to evaluate, could be encrypted also. Send the computation host, run the computation on the encrypted data, generate an encrypted result. And this is one thing that's particular about the model that we're using, is generating an encrypted result that we can then send to the client, and then the client can then perform a decryption operation to get the results as you go from there. So this is the basic model of homomorphic encryption, and there are any number of variants of these kinds of things. And as someone who's an applied cryptographer, this is one thing I'll definitely say, is that there's all kinds of little tricks and optimizations and improvements and generalizations of these kinds of models that you can make, but this is kind of basically the basic model of these kinds of things. And if you have questions about this kind of thing, well, this is one of the nice things about having an unusual name like I do. I'm very easy to find online, so please do reach out to me. So FHE in particular, when it first came out, initial results were not so promising. And this is one of the questions that we get about these whole thing all the time, and I wanted to hand wave through this a bit, was the actual performance of these models and how they run and go from there. And so the very early results by Shai Halevi, Craig Gentry at IBM Research, the very first implementations from back in 2010 were basically doing encrypted basically encrypting bits, running basically a bitwise AND on the encrypted data with something called a bootstrapping operation, and then doing a decryption. And it took on the order of a half hour on a fairly beefy, I think it was a fairly beefy laptop server, like a relatively generic machine, a half hour just to do encrypted bit operations. I got into this basically probably about a month after that result came out, about around then, with my interactions, particularly for DARPA and the U.S. government. And we were actually running, this actually tremendous how much performance has been improving, that we were actually doing full end-to-end encrypted VoIP teleconferencing on stock iPhone 5S's in 2014, which was pretty darn good. YouTube quality audio, definitely good enough to have a singing competition, if not a conversation. And so the performance of these, although homomorphic encryption unfortunately has gotten a reputation for being early on, unfortunately and incorrectly, not as performant as it needs to be. Pretty early on, we were roughly, talk about Moore's law, we were performing, basically improving runtime by an order of magnitude roughly every 6 months or so, ever since. And so about 16 orders of magnitude later, we're starting to build and basically toolboxes of AI techniques running on encrypted data. But the trouble with these kinds of operations and the big lift to get into the space and the big lift to actually make it efficient, for those of you that are interested in it, is that the computations are relatively challenging. And so for those of you that are familiar with a standard compute model, like the RAM compute model, you're probably familiar with the underlying hardware that we have in our computation devices, whether they're phones, whether they're computers, or things like that. Basically have a whole big pile of Boolean logic and state machines on the inside of them, right? And so we as computer scientists, as electrical engineers, as technologists, are trained pretty heavily during our undergrad years to think in terms of finding state machines, thinks in terms of Boolean logic, and RAM compute devices. The challenge with homomorphic crypto and a lot of these underlying encrypted computing techniques, and homomorphic crypto in particular, but other techniques have different approaches, is that these techniques basically all operate on ring algebra. And so they take a very different set of skills to actually go and program these kinds of things. But one of the nice things about them is that they lend themselves very, very well to the kinds of math, statistical operations and things like that, that are particularly germane to modern AI systems and things like that, which is one of the reasons that we are focusing on it, and a number of other folks in the community are focusing on it too. And so relatively naive, so going beyond relatively naive implementations of, for example, risk computations would take on the order of hours to run. And we've seen, basically when I was a professor, I gave one of my students, fresh students, an assignment to go and do that. And someone with a master's degree in computer science from one of the top US universities. And it took them basically hours to run. We basically, since that time, have basically been able to get this down to the order of milliseconds. And so this is just in the order of the past 2 years or so, going from naive implementations that would take hours to milliseconds for relatively simple for evaluations of things like statistical operations, logistic regression type models, and neural nets and things like that. So the world is expanding, and we see this as basically the big opportunity for how to push these things forward and outward. And so we're doing that in a couple of different ways, for both encrypting the algorithms, like I said, encrypting the data, and generating the results from there and moving forward. The team that we actually have doing this, and so like I said, then revisiting the fear and vision of this is the secure collaboration for AI, secure data manipulation, and going from there is the big part of that, and starting to push forward on those kinds of things. And so we're a pretty big cast of characters. Some of the folks that you might have heard these names before. In addition to myself and Alon, Shafi, Goldwasser, Vinod, coming from MIT, Alon and Rina, who are local here to Tel Aviv, and myself based in United States. So I'm very happy to talk about this offline and go from there. So thank you very much for your time.
First of all, thank you very much to Dr. Kurt, but we don't need too much to search for you on the web. You order this for yourself now. You want question? We will give you questions. Now there will be a question from the audience for you. Is anyone have a question to Dr. Kurt from the audience? Yes. Come.
Can you do secure processing also for building, for example, neural network, or only for running neural network and decision trees and other AI models?
Excellent question. Thank you very much. So where we are with respect to the fuzzy edge of the innovation right now is that we are performing evaluation primarily of models after things have already been computed on. In terms of the training aspect, which I think what we call the training aspect, we're supporting it for a number of more statistical-based operations, the more deep net type things, and neural nets is the fuzzy edge of what's actually practical and performant right now. So I would say not quite yet for the specific things you talk to, but there are variants of learning type operations that we're supporting securely right now.